Hello, everyone. I'm Antonio Garcia Dominguez. I am a lecturer at Oxford University, a fellow researcher in model-driven engineering, and I will be acting as session chair for this session. We have the pleasure for this session of having Professor Tony Clark, also from Oxford University, who's going to be giving us a talk on multi-level modeling for model-driven engineering. Before Tony starts his talk, I would like to briefly introduce his very long career in model-driven engineering. Professor Tony Clark is a professor of computer science and deputy dean of education in the College of Engineering and Physical Science at Oxford University. He has experience of working in both academia and industry on a range of software projects and consultancies. While at Marconi Research, he was responsible for designing systems for recognizing aircraft behavior, fusing sonar data, and creating the first AI toolkit of its kind in the UK. He has worked on languages for model object-oriented specification and design, including UML 2.0, MDA, QVT, and MOF. He co-founded a spin-out company selling UML-based meta tools and consultancy to companies such as BT, BAS, BSkyB, and Citibank. His recent work addresses meta-modeling and the issue of supporting decision-making and uncertainty in enterprise systems. In addition to his industrial experience, Tony is also an editorial member of the Journal of Software Systems Modeling, the Journal of Enterprise Modeling and Information Systems Architectures, and the Journal of Object Technology. He has edited several special issues, including IEEE Software and SOSIM, and was co-chair of the Models Conference in 2011. He's also PC chair of the Innovations in Software Engineering Conference for 2021. That is it for the introduction for Tony. Tony, the floor is yours. I will just give you a quick warning when you have less than 5 minutes left.
Thank you very much for that introduction, Antonio, and thanks for the opportunity to give this talk. Hopefully everybody can see the slides and hear me, so thanks very much. Okay, so what I want to address is a problem that we're facing across the IT sector. Systems are getting bigger and bigger. Systems are getting much more, have a much higher requirement for adaptation and change and maintenance. And we've always had the problem of reusability, but that problem is particularly acute. So how does the model-driven engineering community address this? The way that I'm going to propose that we address this is in language engineering, and that involves meta-modeling. And I want to review meta-modeling and just say a little bit about some of the key features that I think are important in terms of meta-modeling for language engineering that will lead to the solution to some of these problems. And I want to then focus briefly at the end of the talk on some relatively recent innovations in meta-modeling, which is leading to some new modeling relationships that are emerging. So if we look at this simple illustration here, we've got on the left at the bottom, we've got a database connected to a CRM system. Now, the conventional way of dealing with this is on the right at the bottom, which is to use standard modeling techniques, create a class for the database, create a class for the CRM system. The language that we're using in order to create those classes is shown on the top right, which is the class and attribute. So those are the language constructs that we're using. Now, in actual fact, what we don't really want to do is think about things in terms of classes and attributes. We want to think about things in the terms of the top left, applications and database systems. So we want to be able to create languages that allow us to model these systems. And why do we want to do that? Well, because it allows us to model these things closer to the semantics of the systems that we're building. That will make them more maintainable. If we use languages that themselves are integrated at another language level above, that will achieve the effect of making it more maintainable. and which is what we want to achieve. This graph here shows a challenge, however. We've got the level of semantics along the right there, which is what we're getting with domain-specific languages. So we're creating our own languages to create these models. On the left there, we've got general-purpose modeling languages, and the general-purpose modeling languages offer us greater reuse because they're reusable right across the spectrum of domains. A class can be used to model an infinite number of things. So what we want to do really is get the sweet spot where we get the huge benefit of being close to the semantics of the domain. That will allow us to present things to people in ways that they're familiar with and design things in maintainable ways, but also get the productivity of reuse. So we want to get this an approach to language engineering for modeling systems, which hits that sweet spot of high semantics and high reuse. And I'll gradually touch on more of this as we go through the presentation. So the kind of thing that we want to wind up with is a model-driven organization or a self-referential enterprise. These are similar names for the same kind of goal, which is an organization which is run off its models. And that would be great because we can offer interfaces to those models to the subject experts that own those bits of the organization. But then that raises a problem. How do we get all those models integrated? Because it's no good having them all separate. That will introduce a worse problem. So we're going to have a backplane, which is a meta-modeling backplane, which allows those languages that we design, the domain-specific languages, to be integrated and then subsequently offered as though they're all different for people to interact with and maintain. So this is the aim. How do we get these heterogeneous languages, the domain-specific ones, integrated? Can we structure those languages in a way that makes them easy to work with? And we'll then touch on some new modeling relationships that are emerging from the field. So the first thing to say, I want to go back to basics here, is what might a basis for meta-modeling be? And what we need this meta-modeling basis to be is executable. It needs to be, it needs to support semantics definitions, and it needs to support arbitrary language engineering in the way that I'm trying to get to in the previous slides. Okay, so we need something that's really flexible and will integrate lots of meta levels. So the approach, which is not new, and it goes back to some work by Pierre Conte in a slightly different context, is to create an executable meta model in which everything is an object. So we start off with this model here, which is hopefully familiar. We've got everything's an object with slots, and the values of the slots are objects. We then extend that with classes, but notice the rule there that everything is a subclass of object. All the classes on there is a subclass of object, which means that class is a subclass of object, which implies that our language concepts, our basic language concepts, which are classes in the general sense, are also objects. So we can manipulate classes as much as we like. Classes have attributes that correspond to slots. Now, if we need to extend that a little bit, if we want executability and semantics, and the thing that we add to that, if we want semantics and operability and executability, is operations. And operations have the ability to be invoked in the sense of methods that we know about. Classes have the ability to be instantiated, and new is just an operation. Now, operations, if you turn them into predicates, allow us to set constraints on classes and collections of classes, which is the basis of semantics. It allows us to say, well, when things are well formed. Even it allows us to say when executions of systems are well formed. So it gives us a basis for behavioral semantics as well. But we have to say how the operations are invoked. So what are the rules? Well, we're going to send a message to any object, and everything's an object here. It navigates up the of link, which is the type link from an object to its class. And then it starts looking for an operation with the name of the message that we've sent to. And that's all we need to do. If it doesn't find it, it goes up the parent link. So with that slight external definition, it gives us all the executability and the semantics that we might need for language engineering. So let's have a look at instantiating a class. If we send a class a message new, then it goes up the of link. Well, since class is an object, it goes up to the class, and it finds an operation called new, and then it can invoke it. And we need to sort of seed the system with what new means, but we can do that in a reflexive way, a self-referential way. If we think hard enough, that's possible. And then that gives us the basis for extending this very simple meta model. So let's have a look at how that might work. We'll send a new message to attribute. We want an attribute called X with the type integer. So what happens? Well, it's going to get redirected to the through the of link to the object, which it's an instance of, which in this case is class, and that finds an operation called new because we've seeded it with that, and then that will create a bunch of objects. I haven't told you the magic by which that happens, but it's very straightforward. And it creates a bunch of objects, and those objects are just instances of things that we already know about. And it creates an object which is a slot with a value X for the name of it, and a slot whose name is type, which is the integer the object that we supplied to it, and that is a new attribute that we've created. Okay, so that's the mindset. So let's create a new class in this way of doing things. We create a new class called person with an attribute. Imagine we've just created the attribute as before. We supply that as the attribute, and the parents are object. Well, we've already got that, so we don't need to do anything more there. Goes up the of link, and then creates the bunch of objects just in the same way, following the same rules as we had before. And there are the bunch of objects that it's created following finding the new and invoking it. But if we put our model-driven goggles on in this sea of objects that we're seeing in front of us there, what we actually find is that it's that. So that bunch of objects there, if we put our goggles on, is that class there, which is very familiar to us. That's what we're used to seeing. But what we've got the ability to do now is work at mixed levels. We've got a language that we're working on, which is the original meta model with class attribute and so on, and we've used it to create a new class. So we've gone from one level down to another level. Let's create a meta class now. So we say, this time I'm going to go do again. I'm going to send a new message for a product type, supply an attribute which I've created beforehand, but this time our parent list or parent collection of parents is class, and that's the crucial thing. If you want to be a meta class, if you want to be a language element, you need to inherit somewhere along the line from class. So it goes through that exactly as I showed you before, creates that sea of objects. We put our model-driven goggles on and we see product type. But product type, instead of being an instance of class and inheriting from object as before, it's an instance of class and it inherits from class, which gives us the opportunity, if we follow those new rules, those send rules as we had before, we can send it a new message. And if we send it a new message, it allows us to create a class called gold, which is an instance of product type, which is meta class, which is an instance of class, which is a meta class. And you'll notice that gold has something peculiar attached to it compared to conventional classes. It has a bit of state, but that state, price equals 3000, is set at the language level. So we've created ourselves a new little language here, the language of product types. And we can now instantiate the gold class in the way that we instantiated all the other things. and we create an object with a slot name carrots with 24 as the value. So we've got many levels involved here. We've got M0 down here, M1, M2, M3, and actually we've got M infinity if we wanted to whiz up the self-referential link there. So this is a basis for language engineering. I haven't shown you the constraints that you could do with this, but you could absolutely check constraints if you implement them as predicates with the operations. Here's extending a meta class. We can take our language that we've just defined. It's very simple, but you could imagine a very rich language here. Product type, and we extend product type with a perishable product type, and that's easy to do just in the same way as we're extended class. But it's at the language level below the language level that class is at, and then we can continue in that vein. Notice that we've got a huge number of levels being mixed here, and that's a challenge. It's a challenge because that's, in addition to being a sea of objects, it's a sea of language levels as well. So we need some way of managing all that, and the rest of my talk is really how do we manage the structure of all of that. And there's a couple of suggestions. There are many other ways, and it's a rich seam of research in terms of how we would manage that. And we can go on and do that. So here's one way that we can structure the language engineering that meta model, that very simple meta model, will support, and that is meta packages. And what we want to be able to do is structure our languages into packages, some of which contain languages themselves, some of which are just models, and the languages are called meta packages. So here's a very simple thing. We've got an order processing system, a little model. Now we want to perhaps use that as the basis of generating Java. The Java is on the right there, or connecting to a database system in some way. And in order to do that, we're going to have to treat some of those classes, and these, as it stands in that diagram on the left, they're just ordinary classes. They're nothing different, nothing special. So we need to get this turned into a language. We need to be using a language to do that in order to treat these classes specially, because some of them will be database tables, some of them will not be database tables, and we need to distinguish between the two elements. So we need a language to do that. And we want to, this might be the language, I think entity beans are a bit old hat now, but you get the general idea. We need to be able to treat some of these classes in a special way. Named element is a different thing to a customer, because named element, it doesn't wind up in the database. How are we going to, and we know from what I've just told you that the simple meta model will support all this. We can define that, but it will be in a sea of classes, mixed levels, with no structure attached to it. So how might we achieve that? And this just shows that you can attach semantics to the entity bean language. The semantics are showing you the well-formedness, that some things are failing and some things are not failing. And we haven't really talked about constraints on that. So how might we do that? Well, here's a version of that little meta language that I've shown you with class and object. In this case, object is called element. This is taken from a tool, so it's got some tooling level things in, as well as the pure meta language that I showed you before. But it's basically the same thing. We've got class and attribute there in exactly the same way. But what we've done is we've extended class to be package. And a package, interestingly, has contents. And the contents are just elements. Think of element as object. So we've got a container of things. That container of things might be a container of basic M0 level objects, but it also, because everything is an object, can be a package containing model elements or language elements or meta language elements. So we've created ourselves a package that contains any mixture of elements. And if we use that sensibly, we can use it to structure our language engineering base in terms of the meta model that I showed you earlier. The way that we might do that is to add a meta package to a package. You can see that on the diagram on the right. And the meta package contains the type level elements for the package it's a meta package of. So there's a constraint check there that we can say well formed as, so we're language engineering in the proper sense. And this is how it's been implemented in the tool, but it's a general pattern. XCore is that model that I showed you originally. Beans is the language that we're aiming to create here, and I showed you it in the little diagram of the database model. And the auto processing then sets its meta package as the Beans language. And of course, the Beans language is just a package, so it needs a meta package, and that's the base language model. And there should be a little thing that's self-referential, that XCore has itself as a meta package because it's self-referential. So this gives us a way of structuring our languages as we don't look at them in terms of a sea of meta classes, etc. So that's one approach that will start to give us a language-based approach to model-driven engineering that will start to address some of the issues that I raised at the beginning. So the last thing that I want to talk, this, as I said, it's a rich theme of research in terms of meta modeling and language engineering, but this approach raises an interesting new relationship in models. We're very familiar with the inheritance hierarchy, and we see the arrows with the triangle head on all of our models, and we're using it for specialization. We're also seeing classification in our models, and the classification occurs when you say something is of a particular type. So the customer Fred is classified by the class customer. So this gives us a two-dimensional hierarchy when you open it out to meta modeling, because we're used to several levels in the inheritance hierarchy. With meta modeling, as I've described it to you, we end up with a classification hierarchy through multiple levels of language engineering. And what that then raises is there something which will allow us to merge these two together? And it turns out that there is, and it's quite useful. And it allows us to address the problem of reuse, as I set out in the beginning of the talk. So what we're observing here is that we normally have one relationship for inheritance and one relationship for classification, but actually there is something that was useful for modeling and language engineering, which merges the two together. So I'll just motivate this and introduce it. So if we look here, we've got a model on the left here, which is going through various levels. We've got at the top, we've created a little language for peripheral devices, an instance of which is the type of all printers, an instance of which is the type of all printers of type CPL844, and then we've got a particular CPL844 at the bottom, PS323. Now, when I set out that little diagram at the beginning where I said, you know, there's a trade-off between domain specificity and reuse, what we might be doing here, what we might want to try and do here is at the level of peripheral device, we're being domain specific, but we've got some information that we know will occur all the way down at PS323, which is abstracting that information up into the peripheral device and allowing it to be reused. So what we want to be able to do is give that information in peripheral device that will apply much lower down the classification hierarchy and is inherited through the levels in between. And that's the novelty in terms that we're observing it by merging these two different hierarchies. So if we have a look at the what we wind up if we do that, this is a multi-level model that uses intrinsic properties on classes. And this is an example of something called FMMLX. It's a language that's been implemented in terms of that main meta-modeling language that I showed you at the beginning. It's a language that's been designed by Professor Ulrich Frank, and I'll name check Ulrich at the end. So just if we look, we've got peripheral device, printer, position, and the particular printer that I showed you before. But we've got some attributes, what we would normally say is attributes on peripheral device. Name and read only are traditional attributes, and you'll see those that are instantiated in the class printer, and therefore we've got properties on printer. But look at sales price. Sales price has a number. It has an intrinsic number attached to it. What that is it says that the sales price is a bit of information that only applies when you get to M1. So if we skip through to M1, which is the CPL844, we'll see that CPL844 has a sales price, and that's the sales price of all CPL844s. So we know when we're defining a peripheral device that at M1, which is skipping several levels down, there will be a property that has to have a value. Similarly with serial number and part sales price. Now that applies to operations. We know that in peripheral device, at level 1, there will be an operation, total units in stock, which allows us to calculate some information in terms of properties on the classes at level, at level 1. So this is a new language feature which supports language-driven model engineering in terms of the meta-modeling that I've outlined to you. Those are the key features that I wanted to get across. I wanted to motivate the fact that we really need to use language engineering in our model-driven approaches. And the reason why we need to do that is that we need to have systems being developed in a domain-specific way so that they support the different users, the different stakeholders. But we need to integrate these models and languages behind the scenes so that as far as possible, our big systems are model-driven. They're running off models, and the vision is model-driven organization. In order to do that, we need to move on several technologies and develop approaches for meta-modeling and language engineering. I've talked to a few of them. I've motivated a core meta-model that you could use. It's very simple, but it's extremely powerful. And I've used that in a couple of different ways there to show you what kind of things people are thinking about in terms of language engineering. There's lots more and lots of different approaches within that family of activity. So just a few links here. Formal foundations. It's possible to give that meta language that I showed you as a model a slightly more formal approach, and there's a paper, fairly recent paper, for that sort of gives a calculus and then uses that calculus language to implement a number of different things, including the intrinsics that I've just showed you, and that can then be analysed, and it's a self-reflective calculus in the way that that model was self-describing. So that might be useful if people are interested. There is a tool, it's called XModeler, and the tool supports the FMMLX language, amongst other things, and it allows executable models, and it supports that core meta language for experimentation. The tool is currently hosted at that URL there, and you can download it, and you can get lots of other information about the approach and the various bits of information. FMMLX is described at that website, but I gave you a very simple example of FMLX, but there are lots of big examples of how it's been used with the intrinsics, and this gives you a flavor of how you could take that basic meta language that I showed you and just add on some intrinsics to it, those numbers that I was adding to the attributes. So it's very simple extension, but then that gives you a whole new language which represents a new modeling relationship, the intrinsic relationship that I described. There's some methodological and technical foundations in a couple of books. Some people may be familiar with the Applied Meta Modeling book, which describes a lot of the meta package and the XCore, the core meta language. That's available on arXiv, and super languages is slightly more technical, how you would take this technology and use it in a more programming but still kind of model-driven approach to language engineering. So those two things might be useful to people. I just want to name check Ulrich. A lot of this work, particularly to do with the intrinsics and the FMMLX language, is driven by Ulrich, and the initiative is a collaborative one and ongoing. So you might want to look at Ulrich's recent paper, MultiLevel Modelling, which gives you a lot of information about the background and the motivation. And that's my last slide. I think we should. It would be great if everybody approached large-scale system engineering from a language engineering perspective. To do so, I think we need to be model-driven language engineers. So I'll stop there. Thank you.